University itself. Later on worked and then joined for his PhD, the same Bangalore University, and he started working on optical tweezers. What are tweezers? He will explain you. You may be knowing twist. So from that origin, it goes tweezers. Optical tweezers laboratory was first set up in Bangalore by Praveen and his guide, Mr. Sharath Anantmurthy. They were able to do extremely wonderful experiments staying in Bangalore. It's a difficult scenario for the reason doing research in a Bangalore in a local university, an upfront research is not a joke. So they were able to set up everything from scratch, and they proved themselves. Some of their papers were internationally acclaimed, even today referred by large community of the optical tweezer learners. So after his PhD, Praveen worked in various organizations. He was teaching at Kelly Postgraduate Center and also for a few days in National College Baswangudi. He was associated with the Bangalore Science Forum and also with the B.V. Jagdish Science Center in his own capacity. Apart from this, he has published paper in most renowned journals, and he has visited United States for his presentation, Singapore, and various other countries for his presentation. He has many awards to its kitty, Best Paper Awards and Best Work Award, and many more. So if I go on explaining that, that takes nearly half an hour. But at a very young age, Praveen is a very successful and committed scientist. That is what I wanted to tell you. So right in front of you, you have a senior whom you can emulate actually. So for all the online participants, hope you are hearing. Praveen is a committed researcher. He could have finished his NET examination and joined for a college. That is not a big issue, but he wanted to be in the research field, a serious research field. So presently he is working in university at Glasgow as a postdoctoral research fellow. Earlier to that, he was working at Raman Research Institute, Bangalore. In all these places, he is working with a very eminent scientist. Now, with this brief introduction, I welcome Mr. Praveen on behalf of all of us here. Mr. Praveen, hope you can hear.
Yeah, thank you, and thank you for that kind introduction.
That's nice. We have with us Professor Bellad, head of the Department of Physics. So he has taken all the pain in making this event to start with the success. After the completion also it will be. We have Professor Chelavappa, we have Madam Asha, and we have Nagachampa Jain with us. So, and Madam Netravati, who was tirelessly working for this program. I welcome you all, ma'am. And I also welcome my dear students. Okay. So now with this, we are over to Mr. Praveen. Your time schedule is 10:45, 10:50 up to. Thank you.
Okay. Thank you, ma'am. I'll start sharing my screen now. So is my screen visible? If you can tell me, I can just start my talk.
Yes, it is visible.
Okay. All right. So at the outset, I would like to thank Dr. Y.C. Kamala for this wonderful opportunity. And I also extend my gratitude to Dr. Bellad for taking all the pain to organize this particular talk. And it's again an honor and a privilege to sort of come back and speak at a place where I was once a student. So I feel today I'm coming full circles, and hope I can share with you the excitement that I have had in the past few years working with optical tweezers. So, as I told you, this is going to be an extremely simple introduction to optical tweezers. What I will do is I will assume that most of my audience are first and second year BSc students, and I will pitch this talk at
Yeah,
the level of
Praveen, just
first
a
and
minute.
second. Yes.
There are few people in the general community, from the general community also. That is the outside physics community also.
Okay, okay, fine. So then what I shall do is I will make note of any questions that you may have. You may even drop questions in the chat box. Uh, and I will leave enough time at the end so that we can have a Q&A, quite an extensive one at that. So uh, with that, I'll start my presentation. So I'm presently at the University of Strathclyde. So what you see here on the right side, that's our business studies building. So we are somewhere here on the left. So this is the building I work in. Yeah. Hope my laser pointer is seen. So this is the building I work in. I am somewhere in the second floor here, and I am in Glasgow in the United Kingdom. So that's where we are in Glasgow. And on the right side here, you see a wonderful picture of the town of Glasgow. So the waterfront here is the River Clyde. As many of you would be knowing, Glasgow used to be a shipbuilding mecca. Mostly 1/3 of all the world's seagoing ships were used to be built in Glasgow at one point in time. Now Glasgow is a city known for a lot of its IT hubs, and again, just like Bangalore, it has sort of grown into a multicultural and a really cosmopolitan city. What you see here is something called as the Armadillo. So it's the Clyde Auditorium. And this particular building here, that is called as the SSC Hydra. So that is your mm, science museum, so to speak. So they have a fantastic science museum, and please make it a point to visit the science museum here, the SSC Hydra, if you're ever in Glasgow. Right. So just half an hour, in fact, from our university is this wonderful location called as the Loch Lomond. I'm sure you would have heard of it. If you travel further north from Loch Lomond, you will see that bridge, which you often see in Harry Potter's movies. Okay, so there's a lot of fun activities to do if you are into hiking and trekking, and you are based out of Glasgow. Okay, so with that, I will get into my talk. So what is a tweezer? As Madam just pointed out, tweezer is a so tweezer. I am sure you would have seen is what is called in Kannada as a chimta. So something used to pick up very tiny particles, and sometimes also used to pluck hair or fix your eyebrows. So that's what a tweezer is. So it's a mechanical device. So I'm now telling you that it's possible to do the same thing with light, albeit with particles that are of size comparable to the wavelength of the light that is being used. Right. So we know that light can push small particles. So in fact, when you go out and stand in the sun, the sunlight falling on you, uh, that sunlight is actually exerting some pressure on you, but that the force with which the light will be acting will be of a piconewton. Piconewton, mind you, is 10 power minus 12 newtons. And as you can well imagine, it's an extremely tiny force, and it is not going to have any noticeable effect whatsoever on you. However, if we were to say shrink you down to the size of a micrometer, then you will definitely feel the force of light. Then you will feel the force which is enough to sort of push you around. Where do we see this in nature? We see this in the case of comets. So comet, as you know, has an icy core and a gaseous tail. So the tail gets blown out. It elongates when the comet approaches the sun. So this is because of an increase in what is called as radiation pressure, that is pressure due to light, which, as I was just explaining, sort of pushes out all the gaseous and icy matter from the core into an extremely long and beautiful tail of the comet. So fine. So light can therefore push small particles. Can it hold or can it trap small particles? The answer is yes. So what you'll have to do in order to achieve trapping with light is you'll have to focus that light. You'll have to focus it down to an extremely tiny spot. So typically, if you take a pointer laser and hold it on the screen, the size of that laser spot is something like 1 or 2 or at most 3 mm. That's the diameter of that laser spot. So now, if you were to sort of use what we call as a high numerical aperture objective, and you are to focus that light down to the size of a micrometer, then it is possible for you to trap any small particle that's in the vicinity of that 1 micrometer spot. So this is what I mean by strong focusing. So we started out with mm, so 1 or 2 mm of laser spot. So that's like 10 power minus 3. And we focused it down to the size of a micron. That is like 10 power minus 6. So we have reduced the size of the laser spot by about 1000 times. So that is what I mean by strong focusing. It's indeed possible to achieve this with what we call as a high numerical aperture objective. Numerical aperture, mind you, is a term that tells you how strongly you're going to be able to focus light. So higher the numerical aperture, higher is your capacity to focus light, which means smaller is the spot that you get. Okay, so when you do that, all right, so let's assume that here is my laser beam here in this picture, and I have an objective lens, a high numerical aperture objective, and that is sort of focusing the light by some 2 or 3 orders of magnitude. That is, it's bringing it down the focal spot by about 100 or 1000 times. When that is done, along with the radiation force that I just explained just now, which we also called as the scattering force, we also get something called as the gradient force. So gradient force is something you achieve only when you strongly focus the laser spot. So what does the scattering force do? The scattering force sort of pushes the particle along the laser propagation direction. Whereas the gradient force, it tries to bring or pull the particle towards the focus. So that is what you're seeing in this particular picture, which I've called as B. So when this force, that is the pulling force, the gradient force, exceeds or dominates the scattering force, you are able to trap the particle in 3D. So that's how you achieve trapping. So what does it take to achieve trapping? You'll have to focus light very strongly. you'll have to bring down the size of the laser spot by about 100 or 1,000 times. That is what we mean by strong focusing. Right. Sorry, not able to browse to, yeah. So as I was explaining to you, so you have the Gaussian beam, and if you look at its intensity, it's maximal at the center, right? So that's what this plot here indicates. And as you move away from the center, the intensity, rapidly decreases. So when you have such a beam focused very strongly, so here the light is traveling from, say, left to right. So along the line, along which I'm moving my pointer. So if we have a small microsphere, a small bead, it could be made out of glass or it could be made out of some plastic material like polystyrene. What happens is that as it approaches the laser spot, it gets pulled towards the focus. So which we show here in B. So what's happening? What's happening is that light is being refracted by the glass bead or the polystyrene bead. And as you can see here, you have different amounts of forces being exerted across the diameter of the bead. The thicker arrow here indicates a higher force. Why is it higher? Simply because that corresponds to light rays that are emanating from the center of the Gaussian beam, where the intensity is high. And this particular ray over here, I've indicated it with a thinner vector arrow, just to indicate to you that this corresponds to the edge of the Gaussian beam profile where the intensity is smaller. So the thickness of the arrow is representative of the magnitude of the force. So this particular arrow changes its propagation direction. This is because of refraction. You can find out by what angle it refracted using Snell's law. And once you have two vectors like that, you can then compute the net force, which is going to be towards the center like that. So over here, if you see carefully, the center of the bead is somewhere here. And if I were to drop that down vertically, correct? So I'm not exactly aligned with the center of the Gaussian beam profile. So I'm somewhat offset by about one radius, I would say, with regards to the center of the Gaussian beam profile. All right. So this is basically the principle behind optical tweezing. Strong focusing leads to unequal forces due to the light rays of the Gaussian beam falling on it. Then you work out a net force and you see that the net force is always towards the center of that Gaussian beam profile. It always moves the bead towards the center of the Gaussian beam profile. Okay. So now, as I told you, off-center rays, that is rays that are bent or focused more, lead to stronger trapping. I will quickly try to play this video. So this is again video that I have borrowed from this particular website. Yeah. So this is actually a simulation, which means that all the things that you see here have been worked out according to actual physics. So we have an iris, so that we are blocking off the extreme rays. So what we have here, therefore, are rays that are coming from the center. The rays from the center are going to bend to a smaller extent. What that means is that the force that I'm going to have on the bead, which is being indicated by the arrow here, the length of the arrow is smaller. So because the force, the trapping force is smaller, the object is oscillating to a much higher extent. So that's what you're seeing here. Okay, maybe we'll play that again. So this is the Gaussian beam profile. I keep an iris in front of it and I block off the off-center rays. That is the rays that would have otherwise bent more. So these are the, so this is suspended in water. That is what it means by refractive index 1.33. And this is, I think, a silica bead. So therefore it has a refractive index of 1.5. And this is the scenario that you will see at time, which is indicated by the timestamp over here. All right. So, and the black arrow indicates the magnitude of the force. Okay. So please commit to memory the fact that this particular bead is now executing a large fluctuation. So now what we'll do is we'll open up the iris. So we had kept the iris so much. So I'm going to take it out so that, I have an extremely small blockage of the incident Gaussian beam profile. Yeah. So that's where the iris is. Okay. It's hardly doing any blocking. So you have these rays from the edge, which are bent by a huge amount compared to these rays at the center, which means we have achieved strong focusing. And because we have strong focusing, please look at the length of the arrow compared to the previous case. It's much larger. The length of the arrow, mind you, is indicative of the trapping force. Now, because the trapping force is huge, the particle is fluctuating to an extremely small amount. Okay, so let's look at that again. So I've opened up the iris so that there is extremely small blockage. So I have these rays which are bent to a huge extent. Larger the extent of bending, higher is the degree of focusing. That's what we understand. And look at the length of the arrow here. The length of the arrow is huge, which essentially means that the trapping force is large. And because the trapping force is large, the particle is fluctuating to an extremely small amount. And these fluctuations, if you ask me, in an actual experiment, are a few nanometers. Okay, so that's like a few atoms lined up. All right. So I think we've looked at them carefully. So we'll move on to the next slide. So this is what I wanted to tell you. So unfocused light, it carries scattering force. Any light, all right, carries scattering force because of photon momentum. Now, when you focus that light, so because of the focusing, you get a gradient force. And we know that any light, focused, unfocused, whatever it might be, will carry some amount of scattering force. So when the gradient force dominates the scattering force, you achieve trapping. So this was the person here who demonstrated optical trapping in 3D for the very first time. His name is Arthur Ashkin. He's one of my scientific heroes. He also happened to be one of the oldest men to have won the Nobel Prize in 2018. And it was given to him at a time when they found that the optical tweezer has sort of become a mandatory tool, if you will, if you are doing any sort of biophysics. Okay, so if you go into any of the biophysics labs today in any part of the world, you will see that somewhere in a corner there will be an optical tweezer setup. Now, these are commercially available, but people find it convenient to build these optical tweezers themselves so that uh, they have so that they have uh, the ability to tweeze biological entities. So when it got to this point, that is when the Nobel Prize Committee decided, okay, I think we must give Mr. Ashkin his Nobel Prize, because each and every biophysics lab you can think of today, at least 90% of them will have an optical tweezer. And not to mention, of course, the pure physics labs where people are studying things like soft condensed matter, for example. Right. So at this point, what I'll do is I'll quickly exit. Okay. Yeah, I'll quickly exit the PowerPoint and try and show an app for you, which I got online, that demonstrates very beautifully what optical tweezers do. You'll have to tell me if you're able to look at my screen. Can you see my screen now? You can tell me yes or no in the chat box, please. Okay, fine. So what you see here is, I think, some bead. It could be polystyrene or silica. The plus there is indicative of the center of that particular bead. So this is the optical tweezer. You've achieved trapping. So what I'll do is I'll switch off the laser. I have made the power 0 here. So there is no optical trap. The particle is put in water. So it is showing Brownian motion. Correct? So this is Brownian motion. It's diffusing in water. So I'll switch on the optical tweezer and you see that it's trapped, right? So let's do the following. So let's say we decrease the laser power and see what happens. So in the previous case, I was playing with the iris, correct? So I had an iris in front of the laser beam. I was opening and I was closing it. So now what I'm doing is I'm just keeping the iris fixed, but I am reducing and increasing the power. Okay, so the plus here indicates the focal point. That's the center of the optical trap. The plus on the bead is the geometric center of the bead. So now I'll increase the power to its maximum. You can see that immediately its position, the fluctuations in its position have come down. So we can also have a visualization of this. So we can have, say, a ruler. So this tells you the extent of fluctuations. So as I was telling you, typically in an experiment, we see a few nanometers of fluctuating length. So that's what you're seeing now. You can also see the potential energy. So you can imagine this to be sitting in a potential well. So what is it? So see, any force, any conservative force for that matter, can be written in terms of the potential energy that gives rise to it. correct? So this is what we learn in first and second year PUC, right? So in the same way, uh, you can imagine this particle to be sitting in this potential well, correct? So it is strongly trapped because we have kept it at the highest possible energy. So now what happens is I'm varying or I'm decreasing the power. So because I'm decreasing the power, the potential energy is shallower. It's not a deep trap. Therefore, the particle is going to execute much larger fluctuations. And if I made it completely zero, there's no, potential for trapping. So therefore, the particle is going to just wander off. Now increase the power, make it maximum, and there it is. Okay, so this is again a very nice software which you can download from this website PHET. I think these things could be put up as supplementary material to this talk, and I'm sure Kamla ma'am and others will make these links available to you at a later time. Fine, so let's get back to our talk. I would encourage all students and also those who are interested in learning more to sort of have this little app and play around with it. So there are various other things here. Maybe it's in the interest of time, we will not get into that. We'll just look at the physics of tweezers here. Okay, so let me get back. Right. So this is where we are, and I will start showing you this particular video. So what you see here are multiple optical traps. Instead of one optical trap, you have many optical traps, and these are generated with the help of a holographic technique. And what they're doing here is that they're just demonstrating to you the trapping capability. They're showing you that they can do a lot of cool things. Right? So these are all micrometer sized beads. I think these are all glass beads. Each one of those beads is like 2 or 3 micrometers in diameter. And this entire field of view is like 60 micrometer by 40 or 50 micrometers as the shorter side. Okay. So these are the capabilities of optical tweezers, right? So just a fun video to show you. So there, for example, you can study, sorry, let me go back. So here, for example, you can study the forces of attraction or repulsion between these two particles, correct? So if you observe their positions carefully, you can then, followed by some simple mathematics, you can even determine the charge that is present on those beads. Okay, so that's the physics that you might be doing in such a scenario. Fine. So I told you that most of the biophysics labs have optical tweezers. So this is something that I worked on extensively during my PhD at Bangalore University. However, I will not be showing you any of the data slides from my PhD work. This is again something that I picked up from the internet. So why should we study, RBCs? So red blood cells have this important task of carrying oxygen to various parts of the body. And in doing so, they will have to sometimes squeeze through a capillary which is much narrower than themselves. Mind you, a typical RBC is 8 microns. So if you pull out a hair, a human hair, the human hair is 50 microns in diameter. So an RBC is almost 1/5 of that, right? In 8 microns or even smaller. So such an RBC will have to sometimes squeeze through extremely narrow channels. And if it has to do that, it has to be very elastic, right? So therefore, it becomes important to understand the elasticity of the RBC, to measure the elasticity of the RBC, and how certain disease conditions, such as malaria or even certain pathological conditions, such as diabetes, high diabetes, affect the elasticity of these red blood cells. So how can that be done with an optical tweezer? Here is again another video. So this is from Elliott Scientific Instruments. So they make these ready-made optical tweezers. So what you see here, okay, is a red blood cell with two of those beads that I was talking to you earlier about attached to the red blood cell. So these pluses here indicate to you where the traps are present. So these would be the position of the traps. And if you look carefully, this is being held stationary and this is being moved. As this moves, the RBC was also moving. So in that way, you end up stretching the RBC, and this is where it was done. It was done at the University of St. Andrews, which is not too far from Glasgow over here. Mind you, we had done something similar at Bangalore University, but unfortunately, I do not have anything to show you from my PhD work at this point. But I can show you something very similar, which is presently on your screen. Yeah, let's look at this again. Oh, sorry. Yeah. So we have an RBC. On the opposite ends of the RBC, we have the two beads. We trap the two beads. Yes, now they're trapped. And we move the bead on the right side. The bead is stuck to the RBC. Therefore, what happens is that you end up stretching the RBC. So you know the force with which you're stretching. From these videos, you can measure the extent to which you have stretched the RBC. So you know the stress, you know the strain. So once you know stress and strain, it's simple first year BSc formula to get the elastic modulus. It could be shear modulus or it could even be the Young's modulus, correct? So that's how you measure the elasticity of an RBC. So I should just quickly point out here what we saw in the case of our studies at Bangalore University. We saw that it was possible for us to measure the elasticity of red blood cells taken from a hyperglycemic person. Hyperglycemia is very high blood sugar, and we saw that that person's red blood cell is extremely rigid. It's lost its elasticity. So this explains why, in case of people with very high blood sugar or extreme diabetes, wounds, for example, do not heal fast. They don't heal fast simply because, for repair to happen, these red blood cells will have to carry various nutrients and squeeze through these narrow channels that we are seeing on the screen right now. And because the RBCs have gone all stiff, they've gone all rigid, they're not able to do their function properly. So this is the reason why wounds don't heal, for example, in case of very high blood sugar. Right. So my talk title at least said something about rotating the RBCs. So let's quickly get to that. Oh, sorry. Yeah. So you saw those multiple traps in one of the earlier videos. So there we had beads, here we have RBCs. Yeah. So the description below tells you what they are. So human red blood cells in 3x3, that means he here, optical traps. Yeah. And he's able to move them closer, farther. And he has two traps on each of the RBC. If you look carefully, there are two plus marks. They both indicate the trap position. So what he's doing is he's holding it at one end and he's moving the other one. If you remember the RBC stretching, we moved it along a line, right? So now, yeah, it's just moving it in a way so that, yeah. So you can ask me what's the point of all this? The point of all this is the following. Uh, an RBC is a viscoelastic particle, viscoelastic object. So what do I mean by viscoelasticity? It not only has an elastic response, but it also has a viscous response. So if you want to measure the viscous response, you might want to look at the time delay between applying the force and the time at which you get a response from the system. So such experiments, that is measuring the viscosity of the red blood cell, is something that is achieved by such experiments. So if you are interested, we can again see this. Mind you, these are all YouTube videos, so I have no copyright over it. So if you just go to Elliott Scientific and look at various things that they're doing and get into the optical tweezers bit, you will be able to see all this. Okay. So we are looking at this again because I want to point out something to you. Yeah. So if you look at this particular RBC, top center, it's doing something, it appears completely different compared to the RBC, other RBCs, and it also is doing something slightly different. And it's in fact buckling, and it's not a proper rotation like how you see in case of other RBCs, right? So therefore, what I want to say is, if you want to think of these as naturally occurring rotors, there is a lot of variability within these rotors, as you would expect for any biological sample. Any biological sample will have large variability. And therefore, if you want to make a instrument, a tiny instrument out of it, probably these are not the best candidates. So what are better rotors? With what can you achieve better rotation? So the answer to that is you can make these spheres out of a material called waterite, which is birefringent. Birefringence, mind you, I don't know if you would have been introduced at the pre-university level, but definitely at the first or second year BSc level, you will learn what a birefringence is. Birefringence is a property with which light within the material will have two different velocities. Okay, two different polarizations will have two different velocities. So if you have circularly polarized light going through waterite, you can ask me after the talk is over more questions about this if you have, but for the time being, just imagine circular rotation, circular polarization to be the case where the electric field vector is rotating as it is propagating. Okay. So you have such a light going through waterite. I told you waterite is birefringent. Birefringence means different polarizations have different velocities. Circular polarization can be thought of as a combination of two orthogonal linear polarizations. Okay, two perpendicular linear polarizations. So each will travel at a different velocity. So that means a torque, correct? Uh, force is what moves an object along a straight line. Torque is something that rotates the particle. This again, high school physics. So such a torque is generated on this weight right particle, and that ends up rotating. I'm sorry, I don't have a photo of a rotating weight right, but what you can see is this intensity of light coming from the weight right, which is rotating, and it's showing this beautiful sinusoidal pattern, which is indicative of the fact that it is rotating uniformly. It is maintaining its speed of rotation. So that's what I wanted to get at. All right, fine. So where are these useful? Again, as I told you, if you want to measure the viscoelastic response of the rotating particle of any given particle, rotating it is a good experiment to do, and these are done well with optical tweezers. And these rotating particles, once their rotating properties are known, you can use them to make tiny machines. They're called as lab on a chip. So you have a lab, right? It's in on the size of a room. So you take that entire lab and bring it down to the size of a few micrometers. So that's what we mean by lab on a chip. So you can have lab on a chip kind of applications where you have these very tiny gears and levers. And if you want a rotor in such a case, probably these are good candidates. Okay, so with that, we take leave of the optical tweezers, and this is the second part of the talk where I had promised to tell you a little bit about what you can do as a science graduate. So I'm going to assume that you will probably do a master's after your bachelor's, and I will tell you what are your options once you have a master's degree. So if you are a physics or a mathematics MSc, you can get into teaching, of course. That seems to be the most populous option for students who complete their masters. Or you can even get into data sciences or some artificial intelligence. But here it's assumed that you have significant ability with regards to writing codes and programming. So if your programming is good and you have some understanding of uh, s- uh, some training in math or physics. So you can ask me, how will that help? It will help because it would have honed your analytical thinking, right? So math and physics are the two good courses to do if you really want to hone your analytical thinking, what people also call as first principles based thinking. So you can so that's the reason why physics and math graduates are hired in data sciences. So you can even do artificial intelligence, banking. So again, particularly for math graduates with a focus on statistics, you will be preferred in banking, particularly when it comes to risk assessments of various kinds, right? Also, it turns out that a field in physics called as statistical mechanics also enables you to do various sorts of risk assessments. This is for life insurance or whatever. And then if you are good with building instruments, good with your hands, you can get into medical physics. So it could be as an ophthalmologist, or even working an X-ray machine, or designing an X-ray machine. Or I'm sure there are plenty of examples, and it might not be possible for me to sort of talk to you today about all of them. And then you can, of course, be hired in various government labs like ISRO if you are into space sciences, or even DRDO, for example. And again, there are mining labs. There are labs with regards to leather and uh, leather research. There are geophysics labs. So there are opportunities abound. You just have to keep an uh, keep an eye out for these labs for these jobs when they're announced. So then coming to chemistry, you can get into various kinds of manufacturing. In fact, I know one of my friends who did a chemistry MSc from Mysore University and was hired in his final year MSc, and today he's one of the CEOs of that company. So you can see that there's definitely scope for growth. You can even get into fertilizers, again, government labs of various kinds, and again, teaching. Life sciences, by life sciences, I mean botany, zoology, and even biotechnology. So with an MSc there, you can probably get into pharmaceuticals, again, ecological survey. So again, if you are from, as they call pure life science, like zoology or botany, this will probably be, up your alley. Or you can go into some of the labs that are looking into some sort of agricultural products. Again, there are plenty of government labs, and you can, of course, teach. So this is if you would want to get into a job immediately after your master's. So now if you want to pursue a research, uh, well, again, there are two options. You can give your NET or GATE or various entrance exams and get into a PhD in a national institute. By national institute, I mean institutes like IAC, Indian Institute of Science, or JNCSR, Jawaharlal Nehru Center for Advanced Scientific Research. I'm sure there are plenty of institutes. If top of my head, I can recall at least 250 institutes of eminence, national institutes of eminence across all subjects: math, chemistry, physics, and life sciences in India. And if you could not get into any of the national institutes, you can probably try and pursue your research in the central and state universities. I'm myself, a product of a state university. And we did, at some point, we were one of the leading labs in India with regards to optical tweezers. We are no longer that. We've lost that advantage because optical tweezers have proliferated each and every lab today. And then um, we did do some good science. So it's not that you can you'll have to do your PhD only in a national institute. It's definitely possible for you to do a very good PhD from central and state university also. So wherever you may go, you are better off probably doing a background check of your prospectful guide or supervisor. Just look at their publications and where their PhD is from, and what they have been doing in the past few years. Like in the past 5 years, have they been active? Have they been publishing papers? So this is something that you will have to do before joining a guide. And of course, most importantly, you will have to ask if they are easy to work with, and the human side of the whole thing. So that's equally important as well. Right. So then, if you would want to study abroad, you will probably be required to give GRE or TOEFL. This is I think this is what people expect in most of the foreign universities and institutes. TOEFL is test of English as foreign language. If you're applying to UK, TOEFL is required. Whereas if you are applying to, say, a lab in Germany, your TOEFL is not required. Just your GRE is sufficient. Sometimes what happens, this is true of the US. So if you're headed to the US, they might ask you to do an extra master's simply because the masters that we do in India are not tailored enough to do something very specific. Like, for example, if you would want to do biophysics, uh, they might ask you to do a biophysics master's. Whereas in India, I doubt if there is a biophysics MSc, but that's going to change. I hear that Ashoka University is offering a very good biophysics program, and I'm sure this will slowly be the case at various state universities also across India. Right. And also, if you are wanting to get an acceptance for PhD abroad, it's always good to have a published paper. So, what I would suggest is that when you're here in India, say you've completed your first or even your second semester of MSc, just find out who's doing what within your department and see if you can uh, join a lab, join some faculty's lab or research group, and see if you can do a small project with them. So that's how you should take this forward. And typically, if you are focused and the project progresses well, within a year, by the time you finish your MSc, you will also have a paper, right? And I'm happy to hear that National College Jainaga in its MSc physics program has made it mandatory for all the students to publish a paper, which means that if they are wanting to go abroad, they already have the advantage of having published a paper. And this is, mind you, a huge advantage when you are applying to either Germany or even uh, or even the US. Right. So what after PhD? After a PhD, you can do a postdoc. That's what I'm doing right now. So why is this? Because some of the research institutes, though it's strictly not a rule, it's generally the case. Uh, they expect some foreign exposure. It doesn't mean that if you do a postdoc in India, it's of no use. I'm not saying that. In fact, I have known faculty members who are well established scientists, well established professors who never did a foreign postdoc. Okay, but it's the trend in, if I may use that word, to expect some foreign exposure after your PhD. Right. And when you are at a postdoctoral training, it's also possible for you to start your own research program. So there are options for this in India, and there's certainly and there are opportunities abound abroad also. In fact, when you're abroad, and in fact, at the university that I'm in, I have started applying for a small grant, a small amount of money to start my own research program. Doesn't mean that I'll get my own lab, I'll get to have my own students. It doesn't mean that. It means that I'll have some amount to buy little equipment that I might want, and I will have some amount to, um, you know, uh, move about. That is, say, so I'm now in the UK. If I wanted to go to the US to attend a conference or meet a colleague or start up a collaboration, that is supported as well in this grant. I haven't got it. I'm certainly looking to apply for it. So this is how you should build your career, so that after your postdoc, you will be considered for appointment in various national institutes. And of course, you could, if you perform exceedingly well and the university and your postdoctoral supervisor have a very good opinion of you, you could even be hired as a faculty abroad. You need not come back to India. But I would urge you all to come back to India. Let's build Indian science. Right. So then, apart from a career in research, you can also do writing, you can do outreach, you can talk to young people, you can involve them in science, you can, I know a lot of people, not many, but definitely noteworthy few. Professor Arvind Gupta is an excellent example, who's into building these toys for students. So these scientific toys, which are built to create an interest in students and to explain difficult concepts easily to students. So you could even do that, or you can go to industry. Here, you know, the sky's the limit really, with regards to what you can do with the industry. In fact, to tell you, most of the scientists, all right, who are hired in the industry, an overwhelming majority have PhDs. Okay, or you can go back to teaching. So it doesn't mean that you have to stick to only one career option. You can even switch back and forth. That's also possible. Say you start out in industry and you feel that maybe the working atmosphere is not to your liking, or the whole concept of industry is not to your liking, and you would want to come back to teaching. You can do that. Or you start at a national institute as a young assistant professor, and then you feel that you are probably better off creating a product, or you want to you have that entrepreneurial skill and you want to tap into that, so you make the switch to industry. So lots of those possibilities are open to you. I would urge you all to stay committed to science, and most importantly to stay curious. Science is one field where you never stop learning. You are always learning. It doesn't mean that, oh, I've got a PhD and I've stopped learning. Nothing like that. This is one field where you constantly evolve, constantly learn, talk to your friends, talk to your colleagues, exchange ideas, create collaborations. Science today is international, multicultural, and collaborative. It's no longer, lone scientist sitting in some dark lab doing something which nobody understands. No, that if that's the, you know, uh, if that's what you think of a scientist, well, might have been in the 17th or 18th century, not today. Okay. With this, I'll thank you for your rapt attention, and I can take questions.
Just before the question, I request all the participants to switch on your camera for a while to have a screenshot. Online participants can ask questions in chat box. Please type your questions. Please switch on your cameras. Asif, get ready. Praveen, you can bring down the slide.
I can take the slide down.
Slide down. Later on you can switch on.
Yeah.
Okay. Rest of the participants, please switch on your camera. All of you? ಇಲ್ಲ ಆಯ್ತು, ಬೇರೆ ಇದ್ದಾರೆ ಹೊರಗಡೆ, ಒಂದಷ್ಟು ಜನ ಇದ್ದಾರೆ ಆನ್ಲೈನ್ ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್. ನೀವು ಆನ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಇಲ್ಲ ಇಲ್ಲಿಂದ ಆನ್ ಮಾಡ್ಕೊಂಡ್ರು ಆಯ್ತು. ಆಗಿದೆಯಾ? ಅಲ್ಲ ಕ್ಯಾಮ್ರಾ ಆನ್ ಮಾಡ್ಕೊಳ್ಳಿ ಸರ್. ಹಲೋ, ಅಲ್ಲ 43 ಜನ ಬರ್ಬೇಕಲ್ಲ ಅಲ್ಲಿ. Okay, it's fine. Can you see the questions there in the chat box?
Yes, ma'am. Yeah, there's one question.
Whichever you feel comfortable.
Sure, ma'am. So there's one question here, I think, from Rajat. So
Rajat, are you online?
Rajat Krishna. Okay, maybe I can answer that.
Okay, you can, please.
Hello, Rajaram Krishna says hi. Hi, Rajaram. And then Rajat Krishna's question is the following. What is the maximum mass on which optical tweezers are effective? So that's the question that he's asking. The answer to that would be the following. So the maximum size of the particle that you can trap is like 10 times the wavelength, I would say, or even 20 times the wavelength. So if the wavelength of the light that you're using is, say, 1064 nanometers, which is the most popular wavelength in optical tweezers, that is roughly 1 micrometer. So if you have a trap made out of a 1 micrometer laser light, then probably you can easily trap 20 micrometers. That's the diameter of the particle. Sorry, that's the radius of the particle that you can trap. So more than the mass, it's the radius that becomes important here. So I should mention to you that there are things like acoustic tweezers. So we saw optical tweezers, which is made out of light. Acoustic tweezers are made out of sound. Okay, so again, you strongly focus sound waves, and you can then trap millimeter size particles. So why? Because sound has that wavelength. So whatever might be the wavelength that you're using, 20 times that wavelength, we can say, is the maximum size limit that you can trap.
Adding to this, Praveen, can you hear me?
Yes, ma'am, I can.
You said 1064 nanometer, the most popular wavelength that you are using. That
Yeah. Yeah.
But 1064 lies in
IR.
in
Yeah.
in IR.
Yeah.
So the property of IR is it not contradicting to laser?
Yeah. So there's this interesting property that most of the biological material, they don't absorb IR strongly, and since most optical tweezers are anyway going to be most optical tweezers are anyways going to be used for biophysics research, it makes sense to use 1064, which is in the IR and which is not absorbed strongly by biological material. Because they don't absorb IR, chances of laser or optical tweezer inflicting damage is very small. So therefore, you can hold an RBC that I showed you without damaging that RBC. So that's the advantage of having infrared as the preferred wavelength for building optical traps.
You can pick up next question.
Okay, Rajaram asks me to show something from my own PhD work. I'll just try and do that now.
Hello. Hello.
Yeah. Hi, Rajaram. How are you?
Praveen, how are you?
Good,
Right,
good.
wonderful
Thank you.
talk from you.
Thank you.
If I have not forgot your thesis, because I have seen your thesis, which you have done in State University, as we mentioned.
Yeah.
Even the State University students can do a wonder like you, what you have done right now. So for that, I congratulate you.
Yeah, I mean, most of the credit should go to Sharat sir for that, not to me.
No, that's that's your okay, fine. Fine. So
hello.
Yeah.
That is your modesty. Okay, thank you.
Because we have seen you doing work day and night, and I know how you have been worked out. Yeah, having said that, you have shown us in your thesis.
Yeah. I'm looking for that.
Of the RBC.
Yeah. I'm trying to look for that.
Interesting. Still, I have not forgotten that. So
okay.
Hopefully that could be helpful for our students to see that part.
Yeah. So I will show you 2 videos then. Is that okay?
Yes.
Okay, then that means I'll have to share screen. Just a minute. Can you please tell me if you are able to see my screen? Banta.
Bandila, no.
Okay. Oh, I have not pressed share screen. Just a minute. How about now?
Yes.
Yeah. Okay. Yeah. So let me explain what's going on here. So these flat ones that you see are all RBCs. So these spiky ones that you see are all WBCs. So we are going to trap only the red blood cell because that's our interest. So at the beginning of the video, just a minute, let me pause this. Yeah, so at the beginning of the video, uh, we have not switched on the laser. The laser, so when the laser is off, you can well imagine that the RBC, which is like a flat disk, would want to stay like that because that's so all this is in gravity, right? Earth's gravity would mean that any plate-like object would have its minimum potential energy when it is flat like that. So now once we switch on the laser, from this orientation, it goes to that orientation. So I've indicated the trap site there. So I turn on the laser, so it did that. Okay. Yeah, so why is that important? That is important because just by looking at the time it takes, you can then work out what is the elastic modulus of that particular RBC. So this is what I said. So when I said that we have measured the elasticity of hyperglycemic RBCs, that is RBCs with people with very high blood sugar levels. So because those RBCs are extremely stiff, they take a very less time to flip compared to normal human red blood cells. That is red blood cells taken from healthy people. Yeah, so just that time measurement followed by some simple mathematics, you can extract the elastic modulus. Yeah, so this was the case with human RBC. We are also trying to study something with or at least now I'm not involved in those studies. And okay, I had another video for some reason that it's not playing. It's okay. So maybe I can tell you what it was about. So this was something that we were doing with chicken RBCs. So in the case of chicken RBCs, what we saw, sorry, in the case of chicken RBCs, what we saw was that it does a dual flip. It first flips like that, and then it flips like that. I'll see, try again. If you give me a minute, I can try again to try and play this video. Sometimes they don't work. Try and get this done fast. Yeah, it's working for me. So are you able to see my screen? No.
Yes. Yes, Praveen.
Oh, no, no, no,
Yes,
no,
we can.
no, no, that's not what I had. Okay, for some reason the video is playing, but I'm not able to share the screen. Just give me one more minute. I'll have a last attempt at it. It doesn't work. It doesn't work.
ನಮ್ಮ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಏನಾದರೂ ಪ್ರಶ್ನೆ ಇದ್ರೆ you can put it in the chat box so that you can easily see. You can put LCG.
Okay. It's not working. Fine. So please take my word for it then. So with the chicken, so the chicken RBC is not shaped like the human RBC. It's like a cigar. It's like a basmati rice grain. Okay. What it does is that it does this and it does that. We are just trying to understand the physics of that. Even now. Fine. Yeah. So now there are some questions. I'll quickly read them out and try and answer. Okay. So I think it is Mahesh. Okay, I'm not able to see the full name. So Mahesh is what I make out the first name as. Is it possible to trap particles with the help of light? Is it possible to make a particle move with a high velocity? Sorry. Move with a high velocity closed light using light or radiation. Okay. What he's asking is, can you trap, say, an RBC and make it go at the speed of light? No, that is not possible. If you get into some special relativity, you will see that the speed of light is a property of the photons alone. And I'm not an expert in this field, but what I imagine is possible is you are probably better off with subatomic particles like or even protons. Yeah, protons and neutrons. So if you go into any of these particle accelerators, that is what they do. A particle accelerator is an instrument that will help you accelerate. That is, as you ask it, as you put it, the instrument to make a particle approach the speed of light. Optical trap is not that. Optical trap is just to hold something in place, right? And it need not be an optical trap always. As I just explained, you could even have an acoustic trap. So this is a wave property. Any wave, you focus it strongly in the focal region of that wave, you can trap particles or objects whose sizes are comparable to the wavelength of the wave that you're focusing. I hope that answers you. Then somebody says, couldn't clear entrance exam for PhD. This is Mahesh Rao. How can I? Oh, sorry, I didn't understand the question. Mahesh B. Rao, if you could please ask the question, maybe it's better. Okay, he's saying that he can't, he didn't do, couldn't clear the PhD entrance. And then, yeah, I see Mahesh Bira. Could you please ask your question?
Hello, Mahesh, you can ask the question. Orally, you can ask the question. Okay, fine. Probably is not.
Okay, fine.
Isn't?
Yeah, so if you just the first part of the question, which I understood, I'll try to answer. So if you, not to worry if you haven't cleared any of the NET or GATE. See, some of the guides at various institutes or even universities will have these funded projects. So these are projects that they would have gotten from a central government sponsor. Sorry, funding agency, and they will typically have one or two PhD positions also. So if you clear those interviews, okay, if you clear just those interviews, then the university where you are working in will register you for a PhD. So so if you take the situation of state universities, this seems to be the dominant entry option for a PhD in state university.
Yes, Praveen, our
Yes,
next session is about to start. So
okay,
it was really a wonderful session. Now I request Professor Bellat sir to reflect upon Praveen's talk and to propose a formal vote of thanks. All the students, please be ready. We shall have a group photo. Thank you.
Good morning, everyone present here. I'm H.C. Bellar, and I am here to present vote of thanks for today's webinar. I would like to thank today's speaker, Dr. Praveen Parthasarathi, for sharing and enlightening our students with his knowledge. Today's webinar about optical trapping or tweezers hold twist, pull and rotate small particles with light, and employment opportunities for pure science graduates. Was full of knowledge and interesting things. It gave deep insights into the topic and also revealed some interesting facts. The point where Dr. Parthasarathi told us about what is optical tweezing. Trapping occurs only when a gradient force dominates a scattering force. Thereafter, it was explained, Arthur Oskin, he got the Nobel Prize in the year 2018 for demonstration of optical trapping. And also it was explained about some applications. 90% of the applications finds in biophysics, molecular physics, and also gave an idea of molecular forces. And also it measures the elasticity of RBC by which one can detect or diagnose the sum of the diseases. His special interest in study is RBC. Human RBC is viscoelastic, means viscous and elastic. By measuring viscosity and the elasticity of the RBC, one can diagnose so many diseases. And also explained about career options of science graduates in different fields. I'm pretty sure precious knowledge that speakers gave us will definitely help our teachers and also students in their studies and future. Once again, I would like to thank Dr. Praveen Parthasarathi for taking out time from his busy schedule to share his knowledge with us. Thank you so much, sir.
Thank you,
I
sir.
would like to express our profound gratitude to our principal, Dr. Y.C. Kamla, for giving permission to organize this webinar. I'm happy to express vote of thanks to our staff members who made this webinar grand success. I would like to thank B.V. Jagdish Science Center technical staff and other members for their support. And also I thank Professor Netravati, who worked very hard to make this event successful. And I also thank Professor Cheloppa, Dr. Raja Ramakrishna, and Mumta Madam. I also thank teachers who have attended this webinar online. Last but not the least, I would like to thank all my students for paying your attention in learning. Thank you, one and all.
Professor Bellad for proposing. Just a minute, Praveen. Be on screen for another, just 1 minute. We must thank Praveen another for the reason when he started delivering lecture, it was morning 4 o'clock for him.
5 o'clock.
3:30, 4, 5. Okay. So that shows again the commitment, his love for National College. We need people like you.
Thank you.
Thanks a lot. So
Thank you, ma'am.
we'll meet for a different kind of activities next.